Hello, Physics 20s. I'm going to give a quick overview of static and kinetic friction. So I have a quick demonstration here, if you can see this, and in addition to the notes. But the I take my phone here and I have it on a binder, and as I increase the angle, we're going to talk about angles. As I increase the angle, it doesn't start sliding because of what's called static friction. Static friction exists between two surfaces that aren't moving. So as I raise it up higher and higher, eventually the component of gravity downhill will pull it down. Actually, it's going to go pretty high. There we go, right there. So at that angle right there, I could measure that if I had a protractor, which I don't. But again, so there's static friction between the two surfaces. Finally, it breaks, and then as soon as it starts sliding, that's kinetic friction. Now, the nature of the surfaces is what determines friction. So I wanted you to see the best way to demonstrate friction is like make a fist with one hand and then make a fist with the other. And when two surfaces come in contact with each other, it's like your fists, the knuckles interacting. Because surfaces are actually rough, even ones that look smooth. If you get down to the microscopic level, they're actually quite rough. And there's like bumps and grooves and ridges. And when two surfaces try to slide across each other, they bump and scrape. And if you can see initially, there's the potential for surfaces to kind of interlock a little bit, kind of like your knuckles. And the resistance to sliding, if you try and slide initially, is static friction. And that will increase up to a limit. And then when you break static friction, then you start to experience what's called kinetic friction, and that's where your surfaces rub together. So anyway, if we come back to this little demo here, you can see I've added some duct tape to the surface of this book, and if I place my phone on that now and do the same experiment, it probably will start slide. Oh, there it goes. See, it started sliding a lot sooner as I increase because the nature of the friction between duct tape and the back of my phone is there's less friction there than there is on that surface. So experimentally, we can determine how, or I guess the amount of friction that is between two surfaces. And I want to turn to these notes now because I'll walk you through them. We'll do a couple examples. So at the top here, you'll note that I added a little bit here for static friction. Static friction. Oops, I mean to underline static friction. It occurs between two stationary surfaces. Okay, and it's typically the strongest type of friction, and I'll show you that in just a second. The kinetic friction is weaker, but it happens between surfaces that are moving or sliding past each other. And I already said that it's weaker than static. In calculating friction, we have to use what's called a coefficient of either static or kinetic friction. The symbol for that is mu. This symbol right here is, it's a Greek letter in the alphabet. It looks like kind of a U with a tail at the front. And we have mu S and mu K. I'm driving those really big, but you can see them both listed right there. Oops, I don't want to do there. It's UK, not USK. So these coefficients you'll see them in the formulas really quick, but these coefficients don't have any units. As you'll see, they're a ratio of what's called the normal force, as you remember, to the force of friction. And the two formulas that you need to know are for static friction and for kinetic friction. And the one for static friction is a bit unique because it involves a less than or equal sign. And as you can see there, I know the vertical lines are absolute values. That don't worry about that too much. The force of friction static, FFS, is less than or equal to the coefficient of static friction times the normal force. And the contrast for that is for kinetic friction. This one's a little more straightforward. It's just equal to the force of friction kinetic is equal to mu k for kinetic friction, the coefficient of kinetic friction times the normal force. I want you to see something else before I show you a chart. This is a I guess a graph of the kind or the amount of friction that a mass experiences as it's being pushed. And I want you to note here that initially, as we come up this curve right here, the amount of force is increasing, but nothing's moving. And as soon as you, just like my phone on the book there, as soon as we get to a maximum amount, then we break, I call it, we break static friction, and then you drop to a lower value, and then you can see just kind of, it's a little bit bumpy and it kind of goes up and down because of the variability of the surfaces. But collectively, the overall amount of kinetic friction is much less than the maximum static. And that's how it is. You imagine if there's a box of, a cardboard box on the carpet or something, and you got to give it a push. Initially, you got to push really hard just to get it going. And then when it starts moving, then it doesn't take as much force to keep sliding it. You can try that at home if you want to test out that theory. So when we look at this table right here, it lists a number of different materials, and there's basically an infinite number of materials that you can, or two different surfaces that you can put on top of each other. And you can see here in this list that in essentially every case, the coefficient for static friction is much greater than it is for kinetic. Or not, well, I mean, it may not be much greater, but it potentially is always greater. So in some cases, it's a little closer. But static friction is always, for our purposes, static friction is always greater than kinetic. So back here then, I tried to clarify a bit on what the static friction formula really means. It says there, since the size of the force of static friction can vary from 0 to a maximum, before motion begins, the equation must have an inequality sign. What I like to compress that right here, just where it says static friction can be a value up to or equal to the maximum amount. So it's not like if you push on if two surfaces have a maximum static friction of, say, 100 newtons. If I try and slide something on those surfaces, if I push with 40 newtons, that's not enough to break 100, so it won't move. But it's not like there'll be 100 newtons of friction pushing back. That would be really weird. That'd be like you'd start to push something and then it would push you back, which doesn't happen. So static friction just matches you. It matches the applied force up to a breaking point, and then kinetic friction kicks in. So I want to just sketch here. I started it already. I want to move this in. I want to sketch just a quick free body diagram, because this is how we analyze forces on an incline. I'm going to say that I've got a mass and it's on a 20-degree angle, and I've already drawn the force of gravity down. I guess I could label that. If you remember from our other free body diagrams, the other forces acting on this include one of which is the normal force, which would be up in this direction here, Fn. Okay, perpendicular to the surface. And immediate or equal and opposite of that would be what we call the force of gravity perpendicular. It's the component of gravity that's perpendicular to the incline. And then at 90 degrees to that would be the force of gravity parallel to the surface. Okay, now let me switch back here. So the point is that this force of gravity parallel that we just drew, we could also draw that. Right here, like this, because I like to call that the force of gravity downhill. It's the force of gravity pulling the mass down the hill. And if this mass isn't moving, which some of these examples will be the case, then there would be a force equal and opposite the force of gravity parallel, which is uphill, and we would label that the force of friction static. Okay, because if it's not moving, remember, that's like with my cell phone not moving, the force of friction uphill will balance that out. So in the course of calculating the amount of friction, either we're going to be analyzing kinetic or static. So I'm going to walk through a bunch of those with you right now. We'll do these two examples that are down here, and then I'll let you try the others on your own before I post the answers. So let's look at this sled. This is a sled, and it has waxed hickory runners on a horizontal, dry, snowy surface. Now, in this case, we can use that information because I gave you guys a table on the back here, and so it says waxed. We look for the waxed skis on dry snow, and there's the coefficient for kinetic friction for those two surfaces. Here's the coefficient for kinetic friction if we need it. So let's go back to the question. Because again, you never need to know those values. The coefficients are just numbers, and you'll see that the units cancel out. So there aren't any units for the coefficient. It says calculate the mass of the sled if the applied force of 46 newtons forward causes the sled to start moving. Okay, so if this happens, if it says that the sled starts moving, some students get tricked by that a little bit because they're like, oh, it's moving, so it must be kinetic friction, so I have to use kinetic friction. If it just starts moving, what it means is you just reached the maximum static friction. And then, because up to that point it wasn't moving, and then it just started moving. So if that's the wording, what you're really thinking is this. We would say that the force of friction, static, and in this case, I know I'm writing this a bit clumsy here, it's the maximum amount. So the force of static friction maximum, that will just equal the coefficient of static friction times the normal force. Okay, so that's slightly different than what's up here, because there we have a less than or equal to sign. And truthfully, the majority of the time you are going to be dealing with the maximum static friction anyway. So then it's a lot similar to the force of kinetic friction. So in this case, we are applying a force of 46 newtons forward on the sled. And what we look at then is that's the amount of, or that will break the static friction. So then what that really means is we're exceeding 46 newtons of static friction. We probably just barely got over 46, but anyway. So the force of gravity is the other force acting on this, and the normal force will be equal and opposite that. So that's the important part to see in terms of determining what the normal force is, because the normal force, well, in this case, it'll equal the force of gravity, but in our other examples, if we're on a slope, it'll equal the force of gravity perpendicular, okay? So what we look at then is, because they were using the coefficient of static friction, I'm going to use that 0.06, and the normal force will equal mass times gravity, which in this case, it's an 80 kilogram, oh, sorry, I'm looking at the wrong one. It's the force of static friction is 46 newtons. That's going to equal 0.06 times the mass of the object times gravity. Okay, so sorry, that's maybe blocking my screen here. Yeah, so we can then just solve for the mass. So we divide the right-hand side by 0.06 times 9.81, and we do the same on the left, and then your answer winds up being 78 kilograms. Okay, after we've rounded, of course. So I'm going to leave you with that for now, and I'll post the answers to the other questions as you go, but hopefully that's helpful to get you started with friction.